Hey everyone, welcome to 2.1, the derivative and the tangent line problem. We're going to really define derivatives here, and we'll do a bunch of examples in some other videos. So here is what is happening with calculus. Calculus really grew out of four major problems. One, the tangent line problem. Two, the velocity and acceleration problem, which is from section 2.2 and 2.3, which we'll get into the next couple sections. Max and min problems we'll see next chapter, and area problems. We saw that from before, and we'll also see them again. So you say, okay, great. All this stuff can be solved using limits and the ideas of limits. And who can we really thank for calculus? Well, I'll tell you, Isaac Newton and Gottfried Leibniz. There are two guys. Isaac Newton's kind of like the plastics. He was the popular guy. Leibniz was like the other guy. And actually, there's a video up on the classroom just about the difference between the two and how they're actually feuding. And there was kind of a big deal between them for quite a while, and what Isaac Newton did to really solidify his place in history as far as being the man who created calculus. So anyway, we're going to talk about the tangent line problem here is with a definition. As far as your definition, tangent to a circle, hey, that's easy. Tangent to a curve, it's a little more difficult. So finding the definition, remember from geometry when we said the tangent to a circle is a point, right? So if I have a line and I say it's tangent, it's right there. And then as we go around the circle, the tangent line changes, right? So that's not bad because it only touches the circle at one point, right? Just like this. Doesn't touch it anywhere else, right? Doesn't go across through the circle more than once. But what happens if you have a curve? It gets a little more tricky because now if I say what's tangent at this exact point right here, well, now I have it where it hits here and there, and now it's no longer tangent because it touches the curve at 2 points. But it's tangent here because it only, at this part of the curve, it only hits it once. So they kind of had to come up with some good, better definitions as far as what does it mean to be a tangent. Now we would have called this a secant. Okay, and a secant line is a line that touches the graph at 2 places. So kind of like here and here, this blue line is really a secant line because it touches the graph at 2 spots. Now if we say delta x and f of c of c plus delta x minus f of c, that's the difference in the y's, difference in the x's, and you should say, I've seen this before. This looks a lot like limits. You're absolutely right. It is. Now, what happens when this delta x shrinks down to a small enough number where it almost gets to 0, right? As we approach 0, what happens? Well, that becomes really the slope of the point. Okay, so it's the slope at a single point. Kind of like saying, what is your speed right now? I know what your average speed is, but what's your speed right now? And that'll give you the slope at a single point. Okay, so let's look at the definition of a tangent line with slope m. If f is defined on an open interval containing c, and if the limit as the delta x approaches 0 of the change in y over change of x, which is the same as the limit as delta x approaches 0 of f of c plus delta x minus f of x over delta x, and those are just saying the same thing, right? Change in y over change in x, change in y over change in x. If that is m, if that is the slope m, if that exists, then the line passing through that specific point with slope m is tangent to the graph at that point. Okay, so it is a slope. This is the biggest thing that you can remember. If you forget everything else, you might be able to recall a lot of information if you just remember that derivatives are slopes at a single point. All right. When I hadn't taken this in 10 years and I was trying to remind myself of what to do, I went back and just said this and then tried to figure out a lot of information, and it helps a lot if you can just remember that derivatives are slopes at a single point. Okay, good. Now, let's actually get into the definition of a derivative of a function. The derivative of f at x is given by, and it said f prime of x. If you remember from geometry when we moved an image from here to here, or here to here, we said the new image was f prime, or a prime, b prime, c prime, that kind of stuff. Same idea. F prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. The exact same thing as a limit. And that is provided that limit exists. Okay, now here's a couple other notation things that you should know. First, finding a derivative, one of these things, is called differentiation. Okay, and a function is differentiable if it's differentiable on the open interval. So kind of like open interval for limits and everything is continuous, same thing. So if I want to find a derivative, I'm going to use differentiation to do it. And a function is differentiable if I can find its derivative and it's on the open interval from a to b. Okay, here's some notation that you will see. F prime of x is that one. Okay, the next one is called, I say, dy over dx, or it's differentiable with respect, R-E-S-P-E-C-T. You can listen to that song if you don't know how to spell that one. With respect to x. Okay, so this one is, it's differentiable with respect to x, where x is in the denominator. Okay, we've got y prime, d over dx of the function, and capital D subscript x of y. Alright, so there's some different ones you might see. These first three are probably the ones you're going to see the most. Alright, so there you go. There is the original first look at differentiation and of derivatives. Remember, derivatives are slopes.